These are some of the problems some of you had a problem with on exam 4. I'll go through them quickly because there's a certain time limit that YouTube establishes. I don't want to go beyond that, otherwise I'll be cut off. Problem 7. On a string, the various frequencies that resonate are integer multiples of the fundamental. The fourth overtone is not the fourth frequency, it's the fifth frequency. It's the one that's over the fourth one. And so we divide the frequency of that particular resonant frequency by 5 to get the fundamental frequency, 69.14. Problem 9 deals with the absorption of gamma radiation. There's a gamma radiation attenuation equation. We're told that the intensity is reduced or attenuated by 90%. 90% loss after the radiation travels 0.24 centimeters. That means the intensity at that location is 1/10 of what it used to be. It's 1/10 of I naught. The I naughts cancel. And you can solve this equation for alpha and you can see the result. I'll jump up here to number 10. It's the Doppler effect equation. The heard frequency is 1080. The broadcast frequency is 1000. We have an automobile chasing an ambulance or fire truck. And so that would increase the frequency. So you add the fire truck is attempting to escape. So to reduce the ratio, we must choose the positive sign. Final result for the speed of the ambulance is 16.5 meters per second. Number 12, the change in the decibel level is given by this equation. We see that the decibel level change is 15 dB, negative 15. Substitute in the intensity initially was 3. Solve this equation for I2, and you get 94.87, rounded off to 95 on the exam. Number 15, same equation, delta beta. This time delta beta is negative 12. We rewrite this equation to get the ratio of the intensities is that number, which is that number. Multiply and you get the later or the second intensity is that fraction of the initial one. So the amount of loss is this decimal fraction, 0.93 rounded off to 0.94. So it's a 94% loss. Now coming over to number 18, we have the two speakers along the diagonal distance. The distance is 20 square root. The other distance is 4. Set that path length difference equal to 1/2 of a lambda. Solve for lambda, solve for f, and you get 360. Number 19, we've got at the 3 corners of a square a proton, and a magnesium double plus ion. We wish to calculate the net force on the magnesium ion. Well, I show the two forces. A push by that proton is that way. The push by that proton is that way. They're equal pushes because they're equal charges and equal distances. And so whatever the total force is, it's twice whatever the effect of one is. Well, let's find out what the force is along the diagonal direction. The force is twice what it is from 1. So there's your double the effect. There's your K. There's your charge of the proton. There's 2 times the proton charge. The separation between the proton and the magnesium ion in both cases is that many meters. You get squared. And then to find the component of either one of these forces along the diagonal direction, you use the cosine of 45. And the final result will be some number measured in newtons. And I convert that to nanonewtons, 16.3. Final result is this, the final problem. We have 2 objects that have a charge. The initial force that either one exerts on the other is 3 newtons, but we double one of the charges, so there's a factor of 2 in the multiplier. The other one is increased by a factor of 10%, so it's a 1.1 multiplier, but the separation is reduced by 30%. That means the new separation is 70% of the old. The decimal value is 0.70. It gets squared. Final result is shown on the board. I'll let you look at that for a while. And if you have any questions, you can raise your hand.